Okay, let's get started. Can you hear me? Can you hear me somehow? Okay? I don't think so.
But I don't think the mic is on.
Yeah, I think a couple of seconds. Ah, amazing. So, welcome to Zero to Hero. So, who of you is using Java in production on containers? Cool, perfect. So, I know this is basically a sponsored slot, and I don't want to bullshit you with the marketing stuff. So this is why I picked 3 things you can start using tomorrow to speed up your Java applications in containers and save money and optimize your infrastructure. So my name is Sasha, and I'm a principal solutions architect for containers at AWS. And I spent, a lot of time with containers and with Java applications. And Java is especially interesting and very important because it is around for 30 years now. So this means there's a lot of talent with Java capabilities. There's lots of code around. So this means you also have a huge stack of libraries potentially in your organization. And you have this huge ecosystem in terms of tooling and the libraries. So if you search for a specific capability, the probability is actually pretty high that you find it somewhere on Maven Central, right? And then you have those amazing platforms like Spring Boot and Quarkus, Helidon, and so on that you can use to implement your business logic. And GitHub measured it is basically the second most popular language, and also the Apache Software Foundation, a lot of Java code is produced. But there are a couple of common issues. So typically what our customers see is that applications tend to start slow, especially the initial bootstrapping of an application. There are a couple of frameworks that are a little bit high on resource usage because they're doing a lot of magic in the beginning, like annotation scanning, all those optimization things, and so on. And what they also see is out of memory errors because high memory usage. And if we take a closer look at how Java in a container actually behaves, we'll see that it initializes the environment once and then handles multiple requests with the same instance concurrently. So this means this instance keeps running after request processing and can continue with this request processing. And usually you scale based on metrics or manually. So sometimes if you have a rather static cluster, manual scaling is totally sufficient because you maybe have an event and then you have a lot of requests coming in. Sometimes you can highly dynamically scale on a metrics like CPU usage or memory usage. Memory is always a little bit tricky with the Java applications, or sometimes you can also build your own custom metrics and use then HPA to scale your application using queue back pressure or other things. And today I brought 3 things you can actually apply and use for your Java applications to speed up the whole startup time. First, it is application class data sharing. I'm not sure if you know this. Then there is a head of time compilation using GraalVM. And one thing that is super interesting, it is coordinated restore at checkpoint, which it's called CRaC. So yeah, it's a funny name, I know. And I only want to spend 10 minutes showing slides and then 10 minutes do a little bit of coding and showing the implications. Because, I mean, I can tell you a lot, but it's more impressive to see it actually in working in a product or in real time. So, sharing classes for better performance. So AppCDS is a JVM feature that helps you to optimize the startup time and memory footprint of Java applications. And if you use something like the Spring framework, it offers a feature to allow you to create this CDS archive for an application upon its exit. So this feature can be useful for optimizing the application startup time by pre-computing and archiving certain, let's say, data structures which reduces the amount of work required during subsequent application launches. And the Spring Boot 3.3 introduces CDS support. And with Java 25, which is coming in approximately mid of September, there will be basically a new iteration of it called AOT, which will be pretty interesting. And the great advantage of CDSs, there is no changes need to be made to the source code. So this means it is basically a feature that you can just apply by changing metadata a little bit. When we talk about ahead-of-time compilation using GraalVM, we have to take a closer look at how the Graal compiler works. And this is basically a dynamic just-in-time compiler. And it's written in Java that transforms bytecode into machine code. And the Graal compiler integrates with the so-called Java Hotspot VM, which supports a compatible version of the JVM compiler interface. And it does so by static analysis of your code. So it only uses the information that is available at compile time. And this is really important because sometimes libraries or, let's say, extensions create bytecode during runtime. So let's say you have your typical APM tool that is attached as an agent to your Java application, and you say, okay, I want to auto-instrument my code. Then what happens it dynamically creates proxies during runtime. That's not working with GraalVM, so this means you need manual instrumentation of your code, so code changes. And this can be a little bit tricky. But if you take a closer look at our results that we have, that we can see here on the right. So startup time, EKS cluster with EC2 instance. So no optimization is approximately 6 seconds, and GraalVM is about 500 milliseconds. So this is huge. So this means especially if you want to scale out quickly, so if you have very spiky workloads, GraalVM can help a lot. So application startup time can be reduced of about, let's say, 90%. Coordinated restore at checkpoint is a different approach. It is basically an OpenJDK project that provides also fast performance for Java applications and immediate startup. And it allows for starting a Java application and a JVM from an image in a warmed up form. So this works in a way that you fire up your JVM, and then you basically do a snapshot of the current state of the JVM and write this to your file system. And then you can restore from that particular checkpoint. And this is interesting because then the JVM is already warmed up. So you basically made a couple of tests and all the branches in your code has been warmed up. So this means you can immediately start from a warmed up JVM. And this is really cool. And basically you have these two things. You have this checkpointing and you have this restore. And this continues from the point when the checkpoint was made. So there are a couple of side effects doing that, because if you checkpoint the current memory state of the JVM, basically everything the JVM has touched, could be also secrets, keys, and so on, are in the snapshot. So from a security perspective, you have to double check if this is working with your code. The other thing is, if you snapshot and then move to a different stage, like let's say from development to integration stage, you have different endpoints for your database and for your queue and so on. So this means after restoring, you have to change the configuration. This can be also a little bit tricky. How this basically works is you have different webhooks that you can use so that you can integrate from an application perspective into the lifecycle of your CRaC-based application. So you have this is CRaC-based, this is CRaC API, and you can implement this API and this interface for those classes that need to be notified that a configuration change happens. So there are only two methods. It's before checkpoint and after restore, which are used as callbacks by the JVM. And if you know AWS Lambda, for Snapstart, we have used this particular interface as well. So it is known for Lambda, developers already using Lambda. So if you want to learn more, we have our Java on AWS Immersion Day. This is basically a complete day full of Java-related stuff. There's also a GitHub repository containing all the code, so you can take a closer look. So you can do this also in your account, or you can ping your account team if you want to run this with AWS. So I've promised that I will show you a little bit of coding, and this is what we're going to do. So this is basically my Visual Studio Code server environment. I hope you can see it. So let's start. I've already deployed an application, and this is basically a very straightforward Java application, just implementing CRaC, so nothing very, very special. And this started in approximately 28 seconds. So I've restricted the application a bit so that I have like approximately 30 seconds of startup time, and I've gave the application the following resources: CPU 256, memory 512 as request, and as limits I've limited to 512 M for CPU, and memory is like 1 gigabyte. So let's start with AppCDS. So what we're going to do is we are basically starting our Maven build, and we're using build packs for it. And build packs has great support for application class data sharing. And now we are basically rebuilding the application. And during the build, what happens is that an archive is created, and this archive is then used during the next start of the application. So we're currently pulling like some build pack images here that we need for that particular build. And in the next stage, what we're doing after this has been built, we are pushing it to ECR and then restart the complete deployment. So you can see, okay, we're just basically checking the configuration for Paketo build for Paketo build packs, and now the build starts. And here is the archive created. So my application is started, an archive is created, and this archive is then stored to disk. So the next thing we're going to do is to push our application to ECR and just do the whole restart. And then we can take a closer look how long it took to start our application. It takes a couple of seconds because it has to add a couple of caching layers. Build is finished. Okay, let's push it to ECR and restart it. So this takes a couple of seconds because we have to stop the old version of the application. So this is just one replica running in our cluster, and then starting the new one. We have 5 minutes left. Enough time. So, okay, now we can take a closer look at the application, and now we can see 14 seconds. So reduce the startup time by 50%. So next thing, GraalVM. I've already prepared something because GraalVM has one particular challenge. It takes quite some time to do the native compilation. So for a standard, not too large applications, it's about 5 to 6 minutes, and you need a really beefy build machine. So typically what customers are doing is they are testing in dev using the standard JVM, and then in later stages applying GraalVM native compilation. And what we have done here is we have basically prepared an image that we're just loading in containerd, and that's it. So next thing we're going to do is to also push it to ECR and do the rollout of the deployment. So basically what we have done also after AppCDS. And then we can also take a closer look how long it takes now. Who has used GraalVM already? Okay, a couple of people. AppCDS? Anyone? One? Okay. I mean, AOT will be really interesting. So. And now what we can see, it's 1.2 seconds. So that's quite impressive. So one of the things we have to do now, we have to copy a couple of Java files, and we have to add one additional dependency, because what we need to do is to add a dependency for the CRaC interface. Exactly, for the callbacks. Now we are going to, no, that's not the right one, this is the right one. Now we have prepared a new Docker file. Oops. And now we're going to build the application again. How this will work is basically we're just compiling our application. The next thing is that we are going to create a CRaC snapshot. And this snapshot is written to our local file system. And then the next step, those files are put into a new container image. And this container image is pushed to ECR. And what we have done here is we have put basically everything into one Docker file because it makes the whole process much, much easier. So the reference architecture we have implemented is using a two-step process, so writing it and then building a new container image, but you can basically put everything into one, which makes it much cleaner. So now the application is started. The checkpoint is created, written to disk, and now it's exporting all the images, exporting to layers, starting to push to ECR, and is restarting the deployment. And then in a couple of seconds, we can see how long it took to start the application. So pending termination in a couple of seconds, should be rolled out successfully. Now we see it's 400 milliseconds. So we brought down from 30 seconds to 400 milliseconds. And my talk is over. Thank you very much.